Hi, my name is Doyeon Kim, and I'll present my work titled Bilateral High-Pass Filters for Robust Deepfake Detection, co-authored by Yonghyun Jeong, Jongwon Choi, and others. The outline looks like this. We'll start off with a brief introduction of our work, and then move on to the analysis on the artifacts, and then go into the details of our approach, and conclude with the results of our study. First, let me briefly introduce the background and motivation of our work. As many of you are familiar with already, deepfake is referred to the AI-generated contents, such as images, videos, and audios. It first emerged in an online community back in 2017, and the word comes from a combination of deep learning and fake. Deepfake in early stages were only about manipulating the faces of celebrities and public figures to say things that they didn't and act in ways that they haven't. Nowadays, however, the target range has expanded to include not only human faces, but almost everything. The technology has advanced to create each pixel of the entire image now, and the result is so realistic that it's indistinguishable in the eyes of human. So, why is deepfake detection such a challenging research topic? Well, first of all, the advancement in generative models is so rapid that new models are released within a very short period of time. Also, due to the nature of data-driven AI models, the detectors can be overfitted to the training settings, which leads to a dramatic performance decline when facing unseen data. This is called the generalization issue in deepfake detection, which makes this research so challenging. However, despite the difficulties, it must be overcome because it's impractical to train the detector with the data of every single newly released generative model. Up next is the analysis of artifacts. First, we analyze the artifact compression map, which compresses the artifacts in the frequency domain to allow adversarial training of the discriminator. Figure 2 illustrates the training process of the artifact compression map. First, the input image is transformed into the frequency spectrum by 2D Fourier transform, and then shifted to obtain the magnitude spectrum map. Then, the bilateral high-pass filters are applied to the map from the pixel level to frequency level consecutively to use the map as the input of the deep neural network to distinguish between the real and fake images. The results show that the artifact compression maps are concentrated in the high-frequency components. Next is the approach of our work. For robust generalization and deepfake detection, we propose a novel approach to utilize the bilateral high-pass filters. Based on the analysis on the artifact compression map, we discovered that the generated images contain the artifacts with different properties in the frequency and pixel domains, as shown in the dark areas in the top row of Figure 1. First, we have found that the artifacts have large magnitudes in the high-frequency spectrum in the frequency domain. Second, we have found that the artifacts are located in the surrounding background of the image in the pixel domain, as shown in the bright pixels in the bottom row of Figure 1. Thus, we propose bilateral high-pass filters to amplify the properties of the artifacts to effectively distinguish between the real and fake images. The frequency level high-pass filter is for amplifying the magnitudes of the high-frequency components, and the pixel level high-pass filter is for emphasizing the pixel values in the background of the images. Next is the experimental results of our model. As shown in the bottom row of Table 1, our model achieves robust generalization with state-of-the-art performance compared to others, even when tested with unseen data outside of the training settings, including the cross-model evaluations. Also, other cross-category experiments in unseen categories of face and horse categories show our model's improved performance compared to other models. Please refer to our paper for more experimental results for more details. This concludes my presentation. Thank you so much for listening. You can check out more information on our work at our GitHub. Thank you.